Well, good morning everyone and welcome to this week's hearings. We're going to begin the week by hearing some presentations from the various expert witnesses instructed by the inquiry. Yes, Ms. Strange.
Yes, Mr. Chairman, thank you. This is the first of 3 days of expert presentations. These will be given by Dr. Barbara Lane, Professor Niamh Nic Dade and Professor Luke Bisbee. As Mr. Millett outlined in his opening submissions, the purpose of these expert presentations is to set in context the factual evidence which will shortly be called in Phase 1. Dr. Lane will be introducing key aspects of the building and its history and will identify the active and passive fire safety measures which were present in the tower at the time of the fire. Professor Nic Dade's presentation will address 3 principal topics. First, the basic science of fire. Second, the element of fire investigation, and in particular what evidence such as fire markings can tell us about the origin of a fire. And third, a summary of her preliminary analysis of the cause and origin of the initial fire within the kitchen of flat 16. Professor Bisbee will be explaining certain key scientific concepts relevant to flammability and flame spread, and will describe the material properties of certain materials present in the facade and the windows in the tower. He will also set out the preliminary evidence which assists in understanding the pattern of flame spread out of flat 16 and over the exterior of the tower on the night of the fire. It is hoped that these expert presentations will assist in setting the framework and context to the factual evidence which will follow, including from firefighters, who will be called first, and from the bereaved and survivors of the fire who escaped from the tower and who will give evidence from September. In terms of the substantive conclusions of the experts in their Phase 1 reports, those will be tested when they come to give detailed evidence in October, and once they have heard and taken account of the factual Phase 1 evidence. It is at that time that the experts will be questioned on the key opinions they have expressed in their reports on Phase 1 issues. At that stage, we will also hear from other inquiry experts, and in particular, Professor Jose Terrero, who has considered the ignition of the facade materials, the fire spread to and on the exterior of the tower, and the fire and smoke spread within the tower. And we will also hear from Professor Purser. He will be dealing with the issues relating to the production of toxic gases, including the toxicity performance of materials present in the tower on the night of the fire. Mr. Chairman, the core participants were informed by letter last week that if they wish to suggest relevant questions for the inquiry experts when they provide their oral evidence, those should be submitted to the inquiry solicitor's mailbox by Monday the 3rd of September 2018. If there are any further questions which arise out of factual evidence heard after that time, then those will need to be provided no later than 5 clear working days before the relevant expert is due to give oral evidence. Prior to calling Dr. Lane, who will give today's presentation, I need to give some trigger warnings about the content of the forthcoming expert material. The presentation of Dr. Lane, which will take place today, will contain images of the tower before the fire and also some detailed images of certain parts of the building after the fire, concentrating on the physical features of, for example, the cladding, the windows and fire doors. There will also be a simulation of a fire in a flat with reference to how Stay Put is intended to operate. The presentation of, I will be calling Dr. Lane today. The presentation of Professor Nic Dade, which will take place tomorrow, will contain detailed images of the flat of origin, flat 16, after the fire, i.e. the burnt out compartment. It will also include videos showing the early development of the fire and thermal images of the firefighting in flat 16, together with the playing of the first 999 call by Mr. Cabede. Mr. Andrew Kinnear QC will call Professor Nic Dade tomorrow. Finally, the presentation of Professor Bisbee, which will take place this Wednesday, will include a large number of images and videos depicting the external flame spread on the night of the fire. This will include the playing of his composite flame spread video, which was played by Mr. Millett in his opening, and detailed consideration of that and of other flame spread material, which shows the tower burning and on fire. Some of the videos include the audio of persons witnessing the fire and their distress at the unfolding events. The presentation will also contain a number of images of the burnt out tower after the fire and the playing of the first 999 call again. Mr. Millett will call Professor Bisbee. So I would now like to call Dr. Lane.
Yes, thank you.
Please repeat after me. I swear by Almighty God
I swear by Almighty God
that the evidence I shall give
that the evidence I shall give
shall be the truth,
shall be the truth,
the whole truth,
the whole truth,
and nothing but the
and
truth.
nothing but the truth.
Thank you very much. Sit down if you like.
Thank you, Dr. Lane. Can you give the inquiry your full name?
Dr. Barbara Lane.
I'm going to put to you a number of propositions which I hope will be uncontroversial. You have provided to the inquiry a preliminary Phase 1 report, which is dated the 12th of April 2018, and which consists of 21 chapters and 11 appendices, A to K.
Yes, I have.
That report addresses, in particular, the active and passive fire protection measures within the tower and the extent to which they failed to control the spread of fire and smoke and contributed to the speed at which the fire spread.
That's correct.
As you indicate in the declaration in section 21 of your report, you have provided it in the same way as you would have provided a report to a court.
That's correct.
In section 1.1 and appendix A to your report, you have outlined your background and experience relevant to the matters in this inquiry.
Yes, I have.
Now we don't need to rehearse all of that in detail today, but I want to pick out some key points. You are a director of ARUP, which is an independent company of designers, planners, engineers, consultants and technical specialists addressing professional services in the built environment.
Yes, I am.
You specialise in fire safety engineering in the built environment, and you have 20 years experience in the construction industry in England and internationally.
That's correct.
You are a chartered fire safety engineer, having graduated from Trinity College Dublin.
Yes, that's correct.
You are a fellow of ARUP, which is an honorary title awarded to exceptional individuals within the firm.
Yes, I am.
And finally, you are also a fellow of the Royal Academy of Engineering and the Royal Society of Edinburgh.
Yes, I am.
Thank you. I outline that, Dr. Lane, so that everyone will appreciate the expertise that you are able to bring to bear and your experience in dealing with the matters that this inquiry has asked you to consider. Are the factual matters set out in your report true to the best of your knowledge and belief?
Yes, they are.
Does your report accurately set out your opinions on matters relevant to this inquiry?
Yes, it does.
Thank you, Dr. Lane. Now, in your own time, please would you go ahead and give your oral presentation?
Okay, thank
And
you.
if you'd like to stand or sit, you do whichever's most comfortable.
I'll move around a bit.
Yes,
Thank
do
you.
that too.
Yes.
All right, thank you.
Okay, good morning. I've arranged my opening presentation into an ordered series of subjects as follows. First, this morning I will start by explaining the original construction materials and the original building form and layout when Grenfell Tower was designed and built between 1967 and 1974. I will provide information on the external landscape around the tower at that time also. I will then provide a detailed presentation on the fire safety requirements for high-rise residential buildings in England. In part 1, I will address the building regulations and the requirement to provide a stay-put strategy, how it is a design condition and why it is not a fire brigade policy. I will address how this is the single safety condition required to be provided. In part 2, I will explain each of the required active and passive fire protection measures that are provided for the stay-put strategy. I will then move specifically onto Grenfell Tower. I will explain the summary timeline I have derived regarding the recorded building works to the tower since 1974, before explaining in chronological order each of the replacement of the passenger lifts, which took place in 2005, the replacement of the majority of the flat entrance fire doors in 2011, a description of the gas supply refurbishment works, which had commenced in 2016 and were still in progress the night of the fire. I will then dedicate the rest of the afternoon session to describing in detail the works that were undertaken on the building as part of the primary refurbishment carried out between 2012 and 2016. This includes a description of the work done to the interior of the building, as well as the works done to the exterior of the building. I will provide an overview and then explain in the following order the external works to the immediate surroundings of Grenfell Tower, the reconfiguration of ground levels to level 3, the reconfiguration of the internal fire main, the refurbishment of the existing smoke control system, the provision of a new heating system and the new hot and cold water systems, before ending with a detailed explanation of the materials forming the rain screen cladding works as I have found them in my work for the inquiry. My colleagues working with me on my factual investigations are Susan Deeney, Peter Woodburn, Tom Parker, Alfie Chapman, Danielle Antonellis and Graham Flint. Dr. Flint is in attendance to operate the series of photos, illustrations and animations throughout the presentation, which we have provided in order to help understand the technical issues I'm focusing on today. The original building construction and layout. As I've explained in section 3 of my preliminary phase 1 report, Grenfell Tower is a 25-storey building with a basement level and a ground to level 23 inclusive, plus a plant room located above level 23 at roof level. It is a residential block built in the early 1970s and is located in the Lancaster West Estate in the North Kensington area of London. The Lancaster West Estate is located in the Royal Borough of Kensington and Chelsea. The estate was designed by Clifford Weirden and Associates in the late 1960s. Phase 1 was approved in 1970 and consisted of the tower as well as 3 low-rise residential blocks called finger blocks. These are Testerton Walk, Hurstway Walk and Barrington Walk. They are 3- and 4-storey buildings. Construction of Grenfell Tower by contractors A.E. Symes of Leighton, London, commenced in 1972 with the tower completed in 1974. To help explain the external spaces around the outside of Grenfell Tower, I have drawn on some additional information not currently in my report, using online mapping services and commercially available context models of the surrounding area. There was a walkway at level 2 of Grenfell Tower that allowed access from each of the finger blocks over to the tower. The finger blocks extend to the south side of Grenfell Tower and enclose 2 large green spaces. The area to the immediate east of Grenfell Tower is Lancaster Green, and there were children's play areas to the immediate west. To the north side lies Silchester Road. Grenfell Tower is owned by the local authority, Kensington and Chelsea London Borough Council. Grenfell Tower was part of their provision of social housing in the borough. The management of social housing in the borough was devolved in 1996 to the Kensington and Chelsea Tenant Management Organisation. Originally, the main fire vehicle access designed for was via Grenfell Road at the south end of the tower. Based on the original design drawings, it also appears that fire vehicles could also have accessed the building via Silchester Road at the north end of the tower if that was needed. As shown in this 3D model, fire vehicles approach the building from Grenfell Road in the south, with access to the southeast corner of the tower provided by driving under the level 2 walkway. In this series of photographs, this southern approach route is shown, which was the state before the last refurbishment works occurred. The height between the road surface and the underside of the walkway structure is approximately 4.8 metres. The presence of the walkway is important in retrospect because it means that whilst it was tall enough to allow fire vehicles to access underneath the walkway for the purposes of internal firefighting, such a walkway provides an obstacle for unplanned external firefighting, as became required during the fire. High-reach appliances would need to move out from underneath the walkway to deploy their ladder or platform and to deploy their stabilisation systems. The area around the east, north and west side of the building were quite open, with a mixture of grassy areas and hard landscaping. It is useful to orientate from the south side, where the 3 finger blocks are located. Originally, outside and around the tower at ground level were positioned a ball game pitch, nursery play areas and other amenity landscaping. From online mapping services, it is apparent that the amenity landscaping around the base of the tower was largely retained until around 2012. In this image, all the areas around the building that could support vehicle access are highlighted in red. In its original form, therefore, fire vehicles could have moved around the base of the tower as follows: 3/4 of the south side, full access to the east and north side, half of the west side. Pedestrians, and therefore firefighters, could additionally reach all parts of the outside of the building originally at ground level, as I have marked here. Originally, there were 3 main pedestrian entry routes into Grenfell Tower. At ground level, firefighters could access the lifts within the central core there. Alternatively, they could climb one of the 3 open stairs external to the tower, up to the walkway at level 2. At this level 2, access was also possible into the central core, to the protected internal stair and the original lifts. Therefore, firefighters would have been able to access the inside of the tower by the walkway. However, fire vehicle access was only provided at ground level. Grenfell Tower is 67.3 metres tall. Originally, it contained 120 1- and 2-bedroom flats. There were 6 dwellings per floor on 20 of the 24 stories, with the other 4 stories being used for non-residential purposes. It was originally intended to house up to 600 people. Levels ground 1 and 3 were more flexible open spaces, which were created for uses such as nursery, offices and a community health centre. Level 2 was left entirely open as a continuation of the walkway connecting to the adjacent blocks of the Lancaster West estate. Each storey in Grenfell Tower is 2.6 metres high, except for level 2, which is 4.3 metres high, and level 3, which is a height of 3.9 metres. Grenfell Tower has a planned floor area of approximately 22 by 22 metres. It has a single, central, reinforced concrete core, reinforced concrete floors, and with perimeter reinforced concrete columns. Reinforced concrete cross walls were provided to separate each flat at level 4 to level 23 inclusive. These walls did not extend to the basement level, nor did these walls exist at ground to level 3. The structural stability mechanism for Grenfell Tower is that of a conventional concrete building with a lateral stability core in the middle of the building and concrete columns around the perimeter supporting gravity loads. The floor is a flat, reinforced concrete slab, transferring load directly to the core. At the perimeter of the building, loads are transferred into the columns directly by the floor and via the precast perimeter beams. Additional support to the floor is provided by the concrete cross walls between the flats. To add further detail to the description I've currently included in my report, the floor slabs were 20 centimetres thick. The walls enclosing the protected lobbies, stairs and lift shafts on every level are collectively referred to as the core walls. The thickness of the core walls vary between 20 and 30 centimetres. The perimeter beams are approximately 25 centimetres thick. The perimeter columns are approximately 70 centimetres square. This does not include the precast ridge facing that was used as sacrificial formwork. This ridged facing, as visible today on the tower, was permanently connected to the columns through the provision of metal wires embedded in the concrete. The structural walls between flats were 20 centimetres thick. The original external wall of Grenfell Tower consisted of exposed concrete surfaces and glazing. The perimeter beams were solid concrete. The opening between each perimeter beam was filled with a combination of sliding windows held in aluminium frames and non-structural, non-combustible infill panels. The specific material of the infill panels is currently unknown, but I understand it to consist of asbestos-bearing cementitious material. As you can see in this photograph, and highlighted by the yellow dotted line, the windows fully filled the space vertically between the top of one perimeter beam and the underside of the next beam. Horizontally, the metal window frames were fixed directly to the concrete structure on 3 sides and to the infill panel on the 4th side. The external wall of the building was therefore entirely non-combustible. The external wall was a single system. This meant there was no void or space concealed within that external wall. From here, I will refer to such spaces, concealed spaces, as cavities. Cavities are spaces enclosed by elements of a building or contained within an element of the building. I will be presenting more information on the issue of cavities in building construction later in my presentation. I now move inside the building to describe the original construction of the window and the external wall internally. Here is a photograph from the inside of a 2-bedroom flat before the refurbishment works were undertaken. This is taken from section 8.4 of my report. The photograph shows the original form of the interior window finishes and the windows themselves. The windows were originally side-sliding, metal-framed windows in a wooden frame fixing system. As I have already noted, these windows and the adjacent infill panels fully filled the space between each perimeter beam from floor to floor. The window sills, the window jambs on both sides, and the head of the window appear to be lined in timber. The original infill panel also appears to have been faced with timber on the room side. Below the windows, a plasterboard covered with a polymeric insulation, a product called pearl board, was applied directly to the concrete perimeter beams. This layer of pearl board was also applied to the concrete ceiling in a small area close to the external wall, but ran along the full perimeter of every room in every flat at ceiling level. Therefore, in terms of combustible material, the original design contained the internal timber surrounds and timber lining of the infill panel, as well as the pearl board above and below the window on the room side. This combustible material did not extend to the outside of the building. Levels ground 1 and 3 contained a nursery at ground floor, community use rooms at level 1, and a health centre at level 3. The layout of levels 4 to 23 were the same on every storey. There were 6 flats on each of these stories. The flats in each corners were 2-bedroom flats, and the remaining 2, one on each side of the core, were 1-bedroom flats. Reinforced concrete cross walls and floors separated each flat on level 4 to level 23. Therefore, each flat was enclosed in fire-resistant construction. This is known as compartmentation, and I will further describe this concept later on. Within the central core was a common lobby that provided access to each of the flats. This lobby also provided access to the residential lifts and the only means of escape stairs, the single escape stairs. This lobby was a separate compartment to the flats and enclosed within its own fire-resisting concrete walls. The original smoke control system used automatic vents on the north wall of the lobby to exhaust smoke into smoke exhaust shafts on the north side, with fresh air being supplied from fresh air shafts through automatic vents on the south wall of the lobby. These smoke and fresh air fans were provided for firefighters to operate if required. The basement has been used since 1974 as a plant space for the various electrical, gas, water and heating systems in the building, with multiple services shafts rising up from the basement through every storey in the tower. Level 24 is roof level. This level had a fully enclosed plant space in the central portion of the storey, with an open walkway around the perimeter of the roof. A ladder was also provided to the roof of this main plant enclosure. There, at the roof of the plant enclosure, was located the outlets from the flues from the basement gas boilers, the outlets from the smoke control system, the outlets from the lift motor room and lift shaft ventilation systems, the permanently open vent provided at the top of the stairs, the outlet vents to the waste pipe stacks serving each of the flats on each of the floors. This ends my explanation of Grenfell Tower and its surrounding area as it was designed and constructed between 1967 and 1974. I will now set out the fire safety requirements for high-rise residential buildings in England, and doing so address specifically the design requirement to provide a stay-put strategy. I will explain how it is designed and how it is intended to operate. After a short break in the second part of this presentation, I will then explain each of the active and passive fire protection measures required to create the safety condition, the stay-put strategy. Building fire safety is dealt with through the requirements of the building regulations. The building regulations state that the requirements shall not require anything to be done except for the purpose of securing reasonable standards of health and safety for persons in or about buildings and any others who may be affected by buildings or matters connected with buildings. The building regulations contains a series of requirements. They are all listed on this slide. Fire safety requirements are dealt with in Part B of the building regulations. Part B, fire safety. The building regulations make clear that approved document B, fire safety, is approved by the Secretary of State for the purposes of the 2000 regulations. Approved document B is therefore what I refer to as the statutory guidance document in my report and in this presentation. Fire safety requirements are considered by means of 5 specific requirements. I have reproduced each one on each of the next 5 slides. B1 deals with means of warning and escape. The building shall be designed and constructed so that there are appropriate provisions for the early warning of fire and appropriate means of escape in case of fire from the building to a place of safety outside the building, capable of being safely and effectively used at all material times. Requirement B2 deals with the requirements to inhibit internal fire spread as it relates to the internal linings of a building. Requirement B3 deals with further requirements for internal fire spread as relates to the structural stability of the building, subdividing a building with fire-resisting construction, and preventing the unseen spread of fire and smoke within concealed spaces. The requirement B4 makes requirements regarding external fire spread, and specifically that the external walls of the building shall adequately resist the spread of fire over the wall and from one building to another, having regard to the height, use and position of the building. It makes requirements for the fire performance of the roof of the building. Requirement B5, the fifth and last of these building requirements, deals with the requirements for access and facilities for the fire services. Specifically, it requires that the building shall be designed and constructed so as to provide reasonable facilities to assist firefighters in the protection of life. Further, it requires that reasonable provision shall be made within the site of the building to enable fire appliances to gain access to the building. There are three other general requirements, but specifically relating to fire safety. First of these three is the requirement to provide fire safety information, Regulation 38. This requires the person carrying out the building work to give fire safety information to the responsible person for that building no later than the date of completion of the work and as reproduced on this slide. The responsible person is the person who owns or controls the building. The required fire safety information to be provided is defined in the building regulations as information relating to the design and construction of the building, which will assist the responsible person operate and maintain the building with reasonable safety. This is for any building where the Regulatory Reform Fire Safety Order applies. This is the legislation that provides for fire safety duties when buildings are completed and occupied. The building regulations relate to design and construction stages only. There is a further requirement for any building to which the Regulatory Reform Fire Safety Order will apply once that building is occupied. That is a requirement to make a full plan submission. This means providing a description of the proposed building work and any other plans necessary to show that the work would comply with regulations. And the final requirement is the requirement of the local authority to provide a completion certificate for buildings to which the Regulatory Reform Fire Safety Order will apply. I note the requirement for a local authority to ascertain, after taking all reasonable steps, that the relevant requirements specified in the certificate have been satisfied. The relevant requirements mean the requirements of Regulation 38 regarding the required fire safety information being provided to the responsible person and the 5 requirements of Part B. I note also that the building regulations currently states that such a certificate is not conclusive evidence that the requirements specified have been complied with. These are the requirements under the building regulations. I would like now to draw your attention to approved document B for fire safety, which is approved, as I said, by the Secretary of State for the purposes of what's called practical guidance with respect to the requirements contained in the building regulations. Therefore, approved document B communicates practical guidance for the 5 fire safety requirements B1 to B5 inclusive. I note it acknowledges that there may well be alternative ways of achieving compliance with the requirements. I have no evidence that such an alternative approach was considered in matters relating to Grenfell Tower and will therefore not mention the concept of an alternative approach again. I will refer to this statutory guidance document, approved document B. Just as the building regulations directly connect design and construction related duties to the Regulatory Reform Fire Safety Order, so too does the approved document make that clear. The approved document B states, for blocks of flats, the Regulatory Reform Fire Safety Order applies to the common parts of blocks of flats only. It advises it would be useful for designers to carry out a preliminary fire risk assessment of the building as part of the design process, and how this fire risk assessment can then be used in the building regulation submission and can be used to assist the Fire Safety Enforcing Authority in providing advice on any additional provisions that may be necessary in the occupied building. However, for high-rise residential buildings, the Housing Act 2005 also applies and exists in parallel with the Regulatory Reform Fire Safety Order. Section 3 of the Housing Act requires local housing authorities to keep housing conditions in their area under review and to investigate and take action against hazards that may be present. Fire is explicitly referenced as a relevant hazard in Section 10 of the Act. Where fire hazards are identified in the common parts of flats, the Act requires the local housing authority to consult the local fire authority where possible before taking action. It is important to note that the Housing Act 2004 states the common parts of a building include the structure and the exterior of the building. Before I explain the Stay Put strategy, it's important to note that the term Stay Put is not used anywhere in Approved Document B. It states, the fire is generally in a flat. There is no reliance on external rescue. Measures in Section 8 provide a high degree of compartmentation and therefore a low probability of fire spread beyond the flat of origin, so that simultaneous evacuation of the building is unlikely to be necessary. And although fires may occur in the common parts of the building, the materials and construction used there should prevent the fabric from being involved beyond the immediate vicinity. It further states these provisions assume that in the design of the building, reliance should not be placed on external rescue by the Fire and Rescue Service, nor should it be based on an assumption that the Fire and Rescue Service will attend an incident within a given time. This approved document has been prepared on the basis that in an emergency, the occupants of any part of a building should be able to escape safely without any external assistance. Approved Document B refers for means of escape from flats to a British Standard, British Standard 5588 Part 1, which is called Fire Precautions in the Design, Construction and Use of Buildings Code of Practice for Residential Buildings. This is no longer current but remains cited in the building regulations. It is now superseded by British Standard 9991 called Fire Safety in the Design, Management and Use of Residential Buildings. BS 9991 does refer to the Stay Put strategy and in 4 specific locations. First, regarding escape, which is almost identical to the text used in Approved Document B. It goes further and refers to occasions where operational conditions are such that the Fire and Rescue Service decide to evacuate the building. This is the only reference in the standard, and no specific provisions are made in order to enable the communication of this change or the management of this change with regard to the provision of active and passive fire protection measures within the building. Secondly, BS 9991 refers to the need for additional protection to the staircase by the provision of smoke control because of the Stay Put strategy. Thirdly, regarding an increase in fire resistance periods for structure for the occupants of other dwellings remaining in place. And finally, it specifically references the Stay Put strategy regarding the fire performance of the external face of the building. It says, flame spread over or within an external wall construction should be controlled to avoid creating a route for rapid fire spread by bypassing compartment floors or walls. This is particularly important, it says, where a Stay Put strategy is in place. And I would like to conclude with a reminder from the very first British Standard Code of Practice for Flats, referred to as CP3, where in 1962 it provided the first explanation of the Stay Put strategy, where occupants, if they choose, remain safely on their own floor, and occupants on the floor on which the fire occurs, and in some circumstances those floors in the immediate vicinity of the fire, should be free to reach safety in another part of the building via the staircase. Since that time, a total building evacuation has not been provided for when designing the active and passive fire protection measures. I have set out each of the statutory guidance document, Approved Document B, and the British standards since 1962, because they all provide the same requirement for active and passive fire protection measures in high-rise residential buildings. I note that while stay put is directly referenced in the British standards, no such mention of it, nor what it relies upon, is provided in the approved document B. I will refer to those published guidance documents at times throughout my presentations today. These published guidance documents are all matters of building regulations. They are not matters of fire brigade policy. The stay put strategy. During a single flat fire, the occupants of that flat evacuate, and all other occupants are safe if they remain where they are. The concept of being safe to remain where they are during a fire is the stay put strategy. It is the single safety condition provided for through the statutory guidance document, approved document B, and all versions of the British standards for flats to date. It is a single safety condition, but with multiple layers of protection provided. These layers of protection, or safety layers, are provided through the required active and passive fire protection measures. So the building construction, including its external walls, the internal compartmentation in the building, and the structural stability system of the building, all the active fire protection measures, such as smoke control to the staircase, and one of the other layers of safety is something I have chosen to refer to in my Phase 1 report as Defend in Place firefighting. Since 1962, CP3 states, the guiding principle in the recommendations which follow is safety of life. In securing this, means of escape, construction and firefighting all play a part. Section 701 goes on to state, in high blocks of flats it is essential that provision should be made to assist the fire service in applying water to a fire as early as possible. The need to apply water early in a fire and the need for the fire being extinguished early are required of the fire brigade. This form of firefighting is provided for by means of the active and passive fire protection measures in the building too. So the building construction, its active fire safety systems and the firefighting in combination provide the safety of life and are the foundation of the stay put strategy. Defend in place firefighting also relies on the high degree of compartmentation in a high-rise residential building because it is this compartmentation enables the single flat fire event upon which the stay put strategy relies. This compartmentation is the very basis of design. I will now narrate an explanation of how the stay put strategy is designed to function in a fire. This is in order to explain how the design of the active and passive fire protection measures, which includes the external wall fire response, provides the safety condition required, which is for the building residents and for the firefighters. The content of this section of my presentation is drawn from sections 3.2, 3.3, 3.4 and section 18 of my report. In the event of a fire in a flat, a fire detection and alarm system should be present in the flat and raise the alarm for occupants in that flat only. No alarm will sound anywhere else in the building. The fire brigade will not be alerted automatically. Once alerted to the fire, the occupants should leave the flat with the door shut behind them. To support this first stage of evacuation from the flat itself, a protected entrance hall is required within the flat. In a single stair building, the person from within the flat on fire must first escape through the common lobby over to the stair entrance. A range of fire protection measures are provided to protect the occupants when travelling through the lobby. Fire-resisting walls around the flat of fire origin, fire-resisting walls around the protected lobby and around the protected stairs, fire doors in the relevant fire-resisting walls, a smoke control system extracting heat and smoke from the protected lobby, designed to prevent smoke from being able to penetrate into the stairs, but providing some local protection in the lobby too. Controls on materials in the common lobby to prevent rapid fire spread through this part of the escape route in the event fire breaks out of the flat compartment. People in adjoining dwellings on the same floor do not automatically evacuate. They have received no alarm or signal to evacuate. The design is focused, therefore, on containing a fire within the flat of fire origin, creating a single flat fire event. This is provided through the fire-resisting walls and floors in that flat. The final side of the fire-resisting box is the external wall. In accordance with the building regulations, the construction of the external walls are required to adequately resist the spread of fire. Therefore, the people in adjoining flats on the same floor who rely on the same horizontal escape route through the lobby are protected, because the design intent is that the fire stays within this one compartment or box around the flat. Everything is invested in preventing the internal spread of fire. The required external wall fire performance, based on adequately resisting the spread of fire, is intended to prevent an external fire scenario beyond the single flat on fire. Equally, people on the floors above the floor where the flat fire has started are also to be protected from the single flat fire below them, again by the measures provided to contain the fire in one flat, again through the compartmentation to the flats, lobby and stairs, along with the lobby smoke control, and again the external wall, and the requirements for the construction of that external wall should also provide protection to the people in the flats above the flat on fire. A person requiring assistance will also need to escape from their flat to the lobby. Once they are out in the lobby, they are now separated from the immediate effects of the fire in the flats. However, protection measures for the lobby are not intended to provide indefinite protection, and it may not be safe for a person to remain within the lobby. At this stage, the choices available to a person requiring assistance to escape are: to escape using the stairs if they are able, to use an evacuation lift with assistance from building management if such assistance is available, to use the firefighting lift with assistance from the fire brigade, to be carried down the stairs by firefighters, building management staff, or potentially their neighbours. There is no provision required in the statutory guidance for residential buildings, unlike other building types, to provide equipment for those persons. So there is no provision made for them to either contact building management, should they even be present in a building, nor to communicate directly with the fire service present in the building. The person can only make a personal 999 call. In other building types, refuges with communication devices are required. Once occupants of the flat on fire have made their way through the lobby, the final part of their evacuation is down the stairs. And once down the stairs, they should now phone 999 and alert the fire brigade to the fire. The protection provided to stairs is intended to physically prevent the penetration of smoke and fire into the stair enclosure by provision of fire-resisting construction, including the stair door. Prevent smoke from entering the stair by provision of fire-resisting lobbies, including the flat entrance fire door and smoke ventilation systems. And so also prevent the spread of fire and smoke, blocking use of the protected stair for any residents above the fire floor. The protection measures in the lobby and the stair, however, are also provided to create a safe working environment for the fire brigade. The fire brigade require this safe working environment in order to be able to access the building, travel up to the flat on fire, and suppress the fire in that flat early. They also rely on the safe working environment in the lobby and the stairs to allow them time and a protected route to travel to rescue any residents in what is expected to be the immediate vicinity of the flat on fire. Nothing more extensive than that is provided for through the building design requirements for the stay put strategy. The requirements of the building regulations to provide active and passive fire protection measures are relied on by all building occupants during a fire, all residents and all firefighters. Since the first Code of Practice for Fire Safety in Flats was published, it states, reliance on such appliances as manipulative types of escape or mobile ladders is considered unsatisfactory. High-rise residential buildings must therefore be designed on the basis that firefighting does not occur from outside. This concept has been carried over into all modern design codes, where the regulations require provisions only for internal firefighting in high-rise residential buildings. Therefore, the building regulations require adequate access to buildings for firefighters and their vehicles only at the entry point to the building and nowhere else around the building. The provisions made for firefighting are also based entirely on an internal fire occurring. By design, these provisions are made on the assumption that a single internal flat fire and contained within the compartment will occur. The construction of the external wall to this compartment is to adequately resist the spread of fire, such that mitigating a spreading external fire is not incorporated into any of the other protection measures in the building as provided for the firefighters. The external fire scenario not happening is critical to maintaining this box around each flat. The high degree of compartmentation is also required for safe firefighting in high-rise residential buildings. Therefore, on the basis of internal firefighting only, approved document B provides for a suitable road access and a parking space for a single fire vehicle within 18 metres of the firefighter entrance and the fire main inlet. It is from here the fire brigade will prepare for internal firefighting operations. Once inside the building, the following is provided for firefighters: a firefighting stair, a firefighting lift, which is a lift can be operated under sole fire brigade control and has safety features to permit it to be used during a fire, a firefighting main, a dedicated system for conveying firefighting water to the upper floors of a building, a protected lobby on every floor, including a smoke control system, a protected space between the firefighting stairs and all flats. The design requirements provide for the following firefighting process. On arrival, the fire brigade will secure a water supply for firefighting from outside the building by means of the required water hydrant in close proximity to the building. The firefighting teams move towards the building and enter. The statutory guidance provides them with a firefighting lift within a protected lobby. The firefighters can approach the firefighting lift and take it under their direct control. The lift is then used by fire crews to carry their equipment, such as hoses, tools and breathing apparatus, and by design is assumed to go to the lobby 2 floors below the fire. This lobby becomes the bridgehead, which is an area used to muster firefighters and their equipment. This lobby is designed to protect the firefighters from fire and smoke on the fire floor above and maintain a safe air environment there. That is air safe to breathe without the protection of breathing apparatus. Firefighters will be tasked with approaching the flat containing the fire and extinguishing it. From within the stair, they connect their fire hose and branch into the building fire main. Firefighters use the protected stair to walk up to the fire floor with a charged hose. They are provided with sufficient water by means of the building fire main provisions, and this includes the provision to charge a second hose, as may be required to protect those firefighters who are now in the flat on fire and suppressing that fire there. The firefighters are now operating within what they term the fire sector. One example of this is a fire sector which includes the fire floor, the floor above and below. The active and passive fire protection measures are required to prevent a fire from significantly spreading beyond a single flat in the fire sector, and I have found it useful to understand how compartmentation is so important when firefighters split the building into sectors. So firefighters rely on the compartmentation and the smoke control to the lobby to also set up any search sectors needed above a fire sector. They rely on the protected stairs and lobby to move safely to any of these required search sectors. They rely on the compartmentation and smoke control within the building to set up what they call the lobby sector, which is below the fire sector and used for coordination of all their required logistics. Again, they rely on the protected stairs and lobbies to move safely up and down to the lobby sector. Finally, the firefighting lifts are provided so they can be safely used during the fire to transport firefighters and their equipment to a floor of their choice. 2 final points. The fire protection measures must be constructed and then maintained to ensure they are fit for purpose in the event of fire. The stay put strategy is provided through design, construction and ongoing maintenance. All building occupants, including the fire brigade, rely on it in the event of a fire. It is the single safety condition provided for in the design of high-rise residential buildings in England. The statutory guidance makes no provision within the building for anything other than a stay-put strategy. There is no means of warning nor a means to communicate the need to increase the areas to be evacuated, as is currently regulated for other building uses. As I explain in my report, I consider the building's stay-put strategy to have failed at 1:26 a.m. and that all events after that time occurred in the context of the total loss of the only safety condition provided for. Thank you.
So we were going to take a 15-minute break at this point.
Yes,
Okay.
that would be convenient, would it? Have a break now?
Yes, please.
All
Thank
right.
you.
We'll stop now for, well, let's say resume at 11:15 sharp. All right? Thank you very much. Okay. Yes, Dr. Lane, when you're ready.
Okay, thank you. Okay, I'm just going to start the second part about fire safety and high-rise. In Table 3.1 of my Phase 1 report, I have provided a full list of the active and passive fire protection measures required through the building regulations for high-rise blocks of flats. A passive fire protection system is one that is an inherent part of the building construction and so does not require any further power, action or intervention to perform its intended purpose. By contrast, an active fire protection measure is one that must undertake an action of some kind, either automatically or manually, in order to perform its intended purpose. Active protection measures typically also require a power supply in order to perform their function. I will first describe the required passive fire protection measures. Buildings are required to be subdivided into fire-resistant compartments to prevent the spread of fire. These compartments are constructed from walls, floors and fire doors required to have fire resistance. Approved Document B defines fire resistance as follows: the ability of a component or construction of a building to satisfy, for a stated period of time, some or all of the appropriate criteria specified in the relevant standard tests. These compartments or fire-resistant boxes are required in multiple locations: the box enclosing each flat, the box enclosing every lobby, the box enclosing any vertical or horizontal shafts, the box enclosing the escape stair. These internal compartment walls and floors protect the occupants of the building. This is achieved by preventing the fire from spreading to adjacent flats or to shared public spaces through the provision of fire-resisting walls and floors and protecting any openings in those walls and floors. Compartment walls and floors are fire tested to demonstrate their ability to prevent the passage of fire and heat. As well as the structure of the walls and floors, buildings also need to contain a variety of different services, such as cables, ducts and pipes. These services need to be able to pass through the building in order for the mechanical services to operate as intended. Openings are therefore created to allow the services to pass through. These openings need to be sealed to prevent the spread of fire through any required fire-resisting compartment enclosure. If a fire-separating element is to be effective, every joint or imperfection of fit or opening to allow services to pass through the element should be adequately protected by sealing or fire stopping, so that the fire resistance of the element is not impaired. Approved Document B defines a fire stop as a seal provided to close an imperfection of fit or design tolerance between elements or components to restrict the passage of fire and smoke. Fire doors are also a form of protection to an opening in fire-resistant compartment enclosures. A fire door is defined in British Standard 8412 as a door which, together with its frame and hardware as installed in a building, is intended, when closed, to restrict the passage of fire or smoke and is capable of meeting specified performance criteria to those ends. As with the tested performance of compartment walls and floors and fire stopping, there are also required methods for demonstrating the specific performance criteria set for fire doors through fire testing. Appendix I of my Phase 1 report identifies 5 specific types of fire door that are critical to maintaining the compartmentation required to support the stay put strategy, as well as support the defend in place firefighting. These are fire doors in a protected stair enclosure, main flat entrance fire doors, protected lift shaft fire doors, the doors within the protected entrance hall in a flat, doors into any fire-protected service shafts. Moving to the external wall component of the enclosure to a flat. This image shows the external wall forming one side of the fire-resistant box enclosing a flat. Regulation B4 requires the external walls are constructed so that the risk of ignition from an external source and the spread of fire over their surfaces is restricted by making provision for them to have low rates of heat release. This is dealt with in section 12.5 of approved document B, which states, the external wall of a building should not provide a medium for fire spread if it is likely to be a risk to health or safety. The use of combustible materials in the cladding system and extensive cavities may present such a risk in tall buildings. External walls should either meet the guidance given in paragraphs 12.6 to 12.9 of approved document B, or meet the performance criteria given in the Building Research Establishment Report called Fire Performance of External Thermal Insulation for Walls of Multi-Storey Buildings for cladding systems using full-scale data from British Standard 8414. That report is referred to as BR 135. So taking each of paragraph 12.6 to 12.9 in turn first. Section 12.6 of approved document B states the external surfaces of walls should meet the provisions of diagram 40. Section 12.7 states in a building with a storey 18 metres or more above ground level, any insulation product, filler material not including gaskets, sealants and similar, etc., used in the external wall construction should be of limited combustibility. And finally, section 12.8 and 12.9 relate to cavity barriers. The approved document B advises the provisions necessary to restrict the spread of smoke and flames through cavities are broadly for the purpose of subdividing A. Cavities, which could otherwise form a pathway around a fire separating element, and closing the edges of cavities, therefore reducing the potential for unseen fire spread. B. Subdividing extensive cavities. In addition, consideration should also be given to the construction and fixing of cavity barriers provided for these purposes, and the extent to which openings in them should be protected. Section 12.5 of approved document B states that as an alternative to following that guidance in 12.6 to 12.9, as I have just set out, the fire performance of the construction of external walls can be determined instead by reference to BR 135. This describes a fire test for external cladding systems so that they can be installed as close to typical end-use conditions as possible and subject to a specific localised fire. So either carrying out this test or complying with the guidance set out in the approved document B is intended to provide the required performance to the external wall of the flat. That external wall should therefore be constructed so that the risk of ignition from an external source and the spread of fire over its surface is restricted by making provision for the external wall materials to have low rates of heat release. That is the provision made for the external portion of the box around each flat. Another passive fire protection measure is the provision of an overall stability system for the building during a fire. I present here the structural form of Grenfell Tower as an example. I described earlier this morning how the floors, walls, beams and columns all contributed to the designed fire stability system. Approved document B states that the load-bearing elements of the structure of the building must be capable of withstanding the effects of fire for an appropriate period without loss of stability. Approved Document B defines this as resistance to collapse, the ability to maintain load-bearing capacity during a fire. For concrete buildings like Grenfell Tower, the structural fire resistance of the structure is achieved through the depth and thickness of the member and a specific depth of concrete insulating the embedded steel reinforcing bars. This combination of concrete and the reinforcing bars provide the stability system. Structural fire resistance is a passive fire protection measure because it requires no power to activate and once installed remains an intrinsic part of the building safety condition. Approved Document B states, the choice of materials for walls and ceilings can significantly affect the spread of a fire and its rate of growth, even though they are not likely to be the materials first ignited. It is particularly important in circulation spaces where linings may offer the main means by which fire spreads and where rapid spread is most likely to prevent occupants from escaping. Therefore, for a means of escape to comply with Regulation B1, capable of being safely and effectively used at all material times, it is required that the surfaces of walls and ceilings within protected lobbies and stairs are materials that restrict fire spread. Additionally, in accordance with Clause 5.19, firefighting stairs must be constructed of materials of limited combustibility. I have described the passive fire protection measures. They are considered to be materials, products and structures. Their required fire performance and how to achieve that performance is then addressed in Appendix A of the Approved Document B. Appendix A describes each of the different classes of performance and each of the appropriate methods of test. Appendix A states, in such cases, the material, product or structure should A. Be in accordance with the specification or design which has been shown by test to be capable of meeting that performance, or B. Have been assessed from test evidence against appropriate standards or by using relevant design guides as meeting that performance, or C. Where tables of notional performance are included in this document, conform with an appropriate specification given in these tables. Therefore, the fire resistance of walls, floors and doors are determined using a standard furnace. I present in this image a furnace designed to undertake standard fire resisting testing on floor systems. This image shows a modern furnace test of a door to determine its fire resistance. The gas temperatures within the furnace must follow the temperature with time profile shown here, reaching 1000 degrees Celsius after approximately an hour and a half. There are a multitude of reaction to fire tests as applied to the performance of the materials forming the external wall, which I have explained in substantial detail in Appendix F of my Phase 1 report. Finally, I present 3 images replicated from the BR135 guide, which shows how it explains the concept of fire spread through external wall cavities, and then 2 photos from the fire test it represents, BS 8414. These photos are a before and after example of a cladding fire test. It is essential that there are no fundamental differences between the tested construction and the designed for construction of an external wall. This is also true of any fire resisting feature, such as fire doors too. Such fundamental differences mean the test evidence can no longer be relied upon to demonstrate compliance with the provisions made in Approved Document B. I will now move on to active protection measures. Approved Document B states, the An active fire protection measure is one that must undertake an action of some kind and typically requires a power supply, as I said earlier. In Appendix G 2.3 of my Phase 1 report, I describe the requirements for residential detection and alarm systems. The design guidance in the approved document B is to provide independent fire detection and alarm systems within each flat, and for the purposes of raising the alarm in that flat only. The minimum requirement for locations of detectors within the flat is within the protected entrance hall. This is intended to sound an alarm when smoke first starts to enter the protected entrance hall in the flat, because this is the escape route within the flat. The intention is that occupants of that flat should have sufficient time to evacuate before the entrance hall becomes impassable due to fire or smoke. Under certain circumstances, a detection system may need to be enhanced by installing additional detectors in the living room and the kitchen, or in all of the rooms in the flat. Where more than one detector and alarm unit is provided in a flat, they must be interlinked so that all of the units sound an alarm on activation of any one device. Approved Document B, Section 5.36 states that all escape routes should have adequate artificial lighting, which illuminates the route if the main supply fails. For a high-rise block of flats, the common lobby and stair shaft require emergency lighting. Emergency lighting is connected to the main lighting circuit in the building for normal power, but it is also provided with a backup battery installed within the light fitting, with the capacity to run the light for a minimum duration of 3 hours in case the mains supply fails. The spacing of emergency lighting is controlled to give a minimum light level over all parts of the escape route in the event of a mains power failure. Smoke control is an important provision to protect escape routes. Approved Document B states it is probable that some smoke will get into the common corridor or lobby from a fire in a flat, if only because the entrance door will be opened when the occupants escape the flat. Therefore, Section 2.25 of Approved Document B states that there should therefore be some means of ventilating the common corridors or lobbies to control smoke and so protect the common stairs. This offers additional protection to that provided by the fire doors to the stair. There are 2 basic types of smoke control system identified in Section 2 of Approved Document B. These are a natural smoke ventilation, and as an alternative to the natural ventilation provisions, mechanical ventilation to the stair or lobby. The Approved Document B refers on to other guidance available for the design of smoke control systems using pressure differentials. This guidance is BSEN 12101 Part 6. This diagram shows a simplified section through a building. A fire has started in a flat. However, the smoke has not yet passed into the common lobby, and therefore the ventilation system has not yet activated. When smoke enters the common lobby, either by leaking through the door or if the door is opened during an escape, the smoke ventilation system is activated by smoke detectors in the lobby. All types of smoke control systems then have common activation process. The vents on the fire floor only remain open. All other vents close. The vent at the top of the stair opens. The fans, if present in the system, start up. If the system uses natural ventilation, then fans are not required. In this type of system, hot smoke rises up a smoke shaft under the effects of natural buoyancy and vents to outside above the roof of the building. A chimney effect is created, pulling air and smoke out of the lobby. An alternative to the natural system is a mechanical ventilation system. This type of system can be designed to use the same kind of shaft as the natural system. However, it relies on an extract fan at the top of the shaft, pulling smoke into the lobby and up into the shaft. The extract fan is signalled to start at the same time as the lobby vents are signalled to open from activation of a smoke detector in the lobby being protected. There is an alternative to this mechanical ventilation system too. This is called a pressurization system. The difference is, rather than pulling the smoke out from the lobby, the fan instead pushes air down and into the stair enclosure. The intention is this air prevents the smoke in the lobby entering the stairs. The smoke in the lobby is then either pushed up a shaft provided for that purpose, or is pushed out of the building through some other opening, such as open windows. Regardless of the type, all smoke control systems are designed to operate for a fire on one floor only. This floor is normally selected automatically by the smoke control system programming, which relies on the location of the detector that has first activated. In addition, a manual override for use by the fire brigade may also be provided on each floor to manually select the floor to be extracted from. The fire brigade may also change where the system is running by using controls directly on the main control panel. These panels are typically located at the ground floor where the fire brigade entered the building. As well as the building requirement to provide a safe air environment for the fire brigade using smoke control, the brigade have their own equipment too, protective clothing and breathing apparatus. Breathing apparatus is required for firefighters to pass beyond the safe air environment of the bridgehead and into the fire sector. The building regulations requires buildings to incorporate adequate smoke protection to the stairs and lobbies, such that this equipment is not required until the firefighting teams are advancing into the fire floor. Firefighting lifts are lifts with specific protection and control mechanisms to permit them to be used safely by the fire brigade during a fire. This figure identifies the key features of a modern firefighting lift. The protection measures for firefighting lifts I will be describing in more detail later on. But it is because of these protection measures to firefighting lifts that Approved Document B also states, where a firefighting lift has been provided to satisfy Requirement B5, this can be utilised as part of a management plan for evacuating disabled people. Any such plan should include a contingency for when the fire and rescue services arrive. I will discuss this again later. Fire mains are installed in a building and equipped with valves, etc., so that the fire brigade may connect hoses for water to fight fires inside the building. Fire mains may be of the dry type, which are normally empty and are supplied with water through hose from a fire brigade pumping appliance outside the building. Alternatively, they may be of the wet type, where they are kept full of water and supplied from tanks and pumps from inside the building. There should be a facility to allow a wet system to be replenished from a pumping appliance in an emergency also. Regarding a dry main, there are two limiting factors in this system: the ability of the fire engine pump to raise water up the building and the amount of pressure that the pipe being used can withstand. With a dry rising main, the further up the building the firefighters are, the lower the water pressure available at the outlet. This is because water pressure is required to push the water up the pipe against gravity. The amount of water pressure that can be introduced into the pipe is limited by the strength of the pipe. Therefore, eventually, a height is reached where the water pressure that can be delivered by a dry main cannot effectively operate a fire hose. For this reason, the statutory design guidance limits the use of dry mains to buildings less than 50 metres in height. In a building which is 50 metres or more in height, there is a requirement to provide a wet fire main. The key differences in a wet fire main are: a tank of water is provided within the building as a water supply for the system. It does not require the fire service to connect the system to an external hydrant. A pump or set of pumps is provided within the building to pump water through the vertical pipe. It does not need a fire service pump appliance. The pumps are automatically controlled to keep the fire main filled and pressurised with water at all times. Therefore, water can be drawn at any floor by the fire service immediately. There is no delay, as occurs in a dry riser, where the fire service must manually charge the fire main when they arrive at the fire. The pumps and the pipes are designed to deliver the minimum pressure deemed required for effective firefighting at the highest floors of the building. So a wet rising main reduces the time required for the fire service to secure firefighting water, and more importantly, is designed specifically to ensure adequate flow and pressure of water on every floor of the building. Performance of this main type does not worsen on the highest floors. The standard for the fire main design, British Standard 9990, states in section 6.3.1 that wet fire main systems are intended to supply 2 outlets at any one time. Therefore, if any more than 2 hoses are used, the water flow and pressure from any one outlet will be reduced. The standard does not make any specific statements on the number of firefighting jets a dry main is intended to support. However, as I have described, the maximum pressure in the main is limited by the ability of the pipe to withstand the pressure being introduced by the fire pump appliance. As more hoses draw water off the main, the pressure and flow to each hose will drop. Fire mains are also designed for a single internal fire event. Whether the main is a dry or wet main, the design guidance for the location of landing valves where the fire brigade plug in to obtain water from is that they should be sited and their outlets directed such that access to them is unobstructed. Personnel can safely lay out and charge hose lines before entering the fire compartment. There is minimal risk of any discharge of water from the outlets coming into contact with lift controls and lift communications equipment or of flowing into the lift well. There is minimal risk of exposure to fire from the accommodation if a door is open. Hoses can be connected, charged and advanced into the accommodation without excessive kinking of the hose line or obstruction to fire doors and exit routes. In addition, the location of the outlets presented in the design guidance has changed over time. When Grenfell Tower was built, the guidance for high-rise blocks of flats was to place the rising main outlet in the common lobby. The current guidance is for the rising main outlet to be positioned in the protected stair. The firefighting hoses for the fire mains are not provided in the building nor through design, but are fire brigade's own equipment. This ends my description of the active fire protection measures. Finally, the presence of these active and passive fire protection measures are intended to create a layered safety approach. They provide the means for early, internal, defend and place firefighting. They provide the means to limit fire and smoke spread from a flat fire out to the lobby and help prevent fire and smoke spread to the escape stair. They create the high degree of compartmentation to support the stay-put strategy in high-rise residential buildings. Those layers of safety are required to prevent reliance on the fire and rescue services for safe evacuation, as so clearly stated in the statutory guidance document. In terms of reference, for those layers of protection are to mitigate the effects of a single flat fire, with minor fire and smoke spread into the adjacent lobby. Those layers of safety are not designed to protect from a multi-storey building envelope fire, nor are they designed to protect from a series of internal flat fires occurring on multiple stories in a building. Such events are not considered as relevant design events in the current terms of reference for those layers of safety. That ends my more general presentations, and I'm now
Yes,
going
thank
to
you.
specifically speak about Grenfell Tower for the rest of the day.
Yes, thank you very much.
In this next part of my opening presentation, I will provide a summary of works undertaken at Grenfell Tower since the building was originally completed in 1974. I have provided a chronology in Appendix D4 of my report of the design and construction of Grenfell Tower, as well as the timing of any significant modifications. The items in this chronology, as relate to refurbishment works on the tower, have been identified using records made available to me, and specifically from planning applications, building regulations applications, fire risk assessments, and other contract documents, including, for example, the health and safety file from the 2005 lift replacement works. I carried out a detailed review of works to Grenfell Tower since 1974 for two specific reasons. First, because I wanted to understand if any significant change to the original fire safety features had been made. And second, to understand the dates of any such changes. This was for the purposes of understanding the appropriate legislation and regulations as may have applied at the time of that change. This was important when analysing the compliance requirements and so the performance requirements for the active and passive fire protection measures in Grenfell Tower the night of the fire. It also helped me understand the range of legislation and regulation as applied to Grenfell Tower, and help me conclude on what, if any, difference in requirements that range created. As I stated in section 3.4 of my preliminary phase 1 report, in respect of all the fire safety measures I have investigated, I have explained my understanding of what was required by the regulations and the relevant statutory guidance at the time of construction of Grenfell Tower. I have also then explained what is required under the current building regulations and its statutory guidance. In this image, I have produced a timeline with the dates of the key changes made to Grenfell Tower since the first recorded works in 1979. I have derived this timeline presented on this slide here from the information contained in a chronology of works submitted by the Royal Borough of Kensington and Chelsea, and through inspection of various contract documents provided to me. The first recorded works on Grenfell Tower was a building regulations application for improvement to the ground floor community rooms in 1979. Between 1979 and 2017, there is evidence of a total of 19 different sets of works undertaken to various parts of the building, including the final refurbishment from 2012 to 2016. For the purposes of this presentation, works include alterations or modifications, or even replacement of, existing elements of the building or its services. I have identified different types of refurbishment work with different colours on the timeline I have provided in this slide. I will now explain those works separated into types. 9 of the 19 recorded changes to the building relate to its internal layout. 3 of those 9 dealt with the residential floors of the building, highlighted in yellow. Specifically, these were the refurbishment of lobbies on all floors in 1985, the refurbishment of levels 3 and 4 in 1986, and finally the works in the primary refurbishment. 5 of the 9 sets of internal layout works dealt only with the non-residential floors. 1 set of internal works undertaken in 1980 was not specific on location. Whilst I have substantial detail on the most recent primary refurbishment, there is little detail available on the specifics of the other 8 sets of internal works that occurred. 4 of the 19 recorded refurbishments included work to the lifts in Grenfell Tower. In 2005, all 3 lifts in the building were fully replaced. This consisted of the 2 main lifts serving all floors and a smaller hydraulic lift that was provided to access level 2 and 3 from ground. To enable these works, additional preparatory work was also needed separately in 2004. These were works to build a new brick enclosure at ground level to contain the new hydraulic lift equipment for 1 of the 3 lifts. The other 2 sets of work on lifts in Grenfell Tower were undertaken as part of the primary refurbishment. First, in 2013, the low-level access lift between ground and level 3 was removed as part of the demolition works to the tower. Then, later in the primary refurbishment, the lift shafts were modified to permit the lifts to also serve levels 1 and 3, where previously they did not. 3 of the 19 recorded refurbishments included work to fire doors within Grenfell Tower. Fire door replacements were carried out within the tower in 1985, 2011, and finally during the final primary refurbishment. The 1985 works replaced an undetermined number of flat entrance fire doors in unknown locations in the building. The building regulations application provided to me and associated with the works did not define the exact number of doors. In 2011, a programme of flat entrance door replacements was undertaken. This involved fitting 106 replacement flat entrance doors to tenanted flats. No works were done to 12 leaseholder flats or 2 tenanted flats. Finally, in the last primary refurbishment, new stair doors, new flat entrance fire doors and fire doors to other rooms were provided on levels ground 1, 2 and 3 only. 2 of the 19 refurbishments since 1974 were to the external construction of the building. Specifically, in 2008, the flat roof coverings at roof level on top of the building were replaced. Then the overcladding of the whole building, which took place from 2012 to 2016. In 2016, 1 gas supply riser running vertically up the building was decommissioned and replaced with a new gas supply pipe. The appointed gas expert, Rodney Hancock, is investigating all aspects of the gas supply to Grenfell Tower and will cover these matters in detail, including the history of gas supply related works to the tower. I have incorporated the most recent works in 2016 only for the purposes of my fire safety related work as they relate to compartmentation. As a result of my understanding of the works carried out to Grenfell Tower since 1974, I provided in section 4 of my report the specific refurbishment works that I consider to be relevant to my investigation of the active and passive systems that existed in Grenfell Tower. This is due to their direct influence on the eventual performance of the fire safety measures on the night of the fire. These are the lift replacement works in 2005, the tenant flat entrance door replacement in 2011, the refurbishment works between 2012 and 2016, and the new tenant gas supply, which was incomplete the night of the fire. I will deal with each of these in turn in the next series of presentations. The first of the relevant works is in relation to the lifts provided in Grenfell Tower, and so the status of that lift provision the night of the fire. Works were undertaken in 2005, as I said, with further works undertaken during the primary refurbishment. Both works are relevant to the fire safety status of the lifts the night of the fire. I will therefore describe the works during both timeframes here. The original plan drawings for Grenfell Tower indicate 3 lifts were installed. As this image shows, this included a small lift connecting ground level to level 3. This small lift was located in the southeast corner of the building. It was ultimately removed as part of the primary refurbishment works, and so I have not considered it any further. The remaining 2 lifts, as you can see, were located centrally in the building, opening out into the lobby between each flat and the single protected escape stair. Access to the 2 main original passenger lifts was provided from the original ground level lobby and at level 2. Access to these 2 lifts on upper floors was provided on every floor between level 4 and level 23. These central lifts did not serve level 1 and level 3. Therefore, these passenger lifts were for the purposes of accessing the floors in the tower with flats only. Before describing the works undertaken to the lifts in Grenfell Tower, I want to first describe the 2 types of lift for firefighting. There are 2 types in the context of Grenfell Tower, because since the tower was built, the requirements for lifts for firefighting has changed. This occurred in 1992. Therefore, understanding the lift requirements for firefighting before and after 1992 is relevant. For lifts to be suitable for firefighting, they require special features to allow the fire brigade to access them during a fire, and for the lifts to be robust enough to continue operating in a fire scenario. Since 1971, prior to the construction of Grenfell Tower, there has been a requirement for the provision of a lift which may be used by the fire brigade within high-rise residential buildings. At that time, lifts with specific firefighting provisions were referred to as fire lifts. In 1992, the name used to describe these lifts changed to firefighting lifts, and the required safety provisions to enable lifts to be safely used by firefighters in a fire was changed also. This term firefighting lift and the associated requirements for such lifts are in general still enforced today. To understand the fire safety features for a lift, it is useful to understand the basic components of a lift system and the terms used to describe it. These are illustrated in this image. People or goods are transported within the lift car, which is suspended by cables directly affixed to the lift car. A lift machine, typically located in a machine room at the top of the lift, drives and stops the lifts. A counterweight is used for traction. The lift is housed within a vertical shaft. Openings in these shafts at each floor of the building allow people to access the lift. The lift landing doors positioned in each of these openings allow controlled access to the lift car and to the shaft itself. The original code of practice for fire safety, as applied at the time of construction at Grenfell Tower, is again CP3, dated 1971, and it describes the provisions to be made for a fire lift. I have illustrated the key features required for a fire lift at the time of construction of Grenfell Tower on this image. The requirements are that the fire lift should serve every residential floor. A fire switch should be provided whereby firefighters can obtain and control the use of a lift without interference from other persons, and the requirement of a maximum distance between the stair and lift of no more than 10 metres. The lift car should have a platform area of not less than 1.5 metres squared, a capacity of 550 kilograms, and reach the top floor from ground level within 1 minute. And finally, the requirement that the electrical supply to any fire lift should be provided by a sub-main circuit exclusive to the lift, with the cable supplying current passing through routes of negligible fire risk. If we now consider the fire safety requirements for a firefighting lift, there is a clear difference in standard. As I have illustrated in this image, the number of features required in a firefighting lift, as required from 1992 onwards, is substantially greater. Of the 15 features required for the new firefighting lift, three of those provisions were also required for the historic fire lift, shown here in blue. They relate to the size of the lift car, the minimum travel time for the lift to reach the top floor, and the provision of a fire switch for the fire brigade. 4 of the 15 required features for a firefighting lift were also required for a fire lift, but a higher standard is now required. I have shown those features in orange. For example, the lift is required to serve every floor, not just residential floors. The power supply is required to be fire protected, not routed through areas of negligible fire risk. The minimum capacity of the lift car has increased to 630 kilograms. And finally, there are 8 additional fire safety features required for a firefighting lift compared to a fire lift, which I've shown in blue-grey here. These are more substantial features. For example, 2 independent power supplies for the lift in case of power failure to the main supply, water protection to the lift, and the provision of an escape hatch to the lift car, fire-resisting landing doors, a 2-way intercom communication device between access level, the lift car, and the machinery room. This was the standard required for lifts used at the time of the lift replacement work in 2005 and subsequently in 2012 to 2016. The standard of lift for firefighting is also relevant to the use of lifts for evacuation. The current version of Approved Document B, which was applicable at the time of the primary refurbishment, permits the use of lifts which meet the standard of a firefighting lift to be used in an evacuation lift. This provision applies to firefighting lifts only and not to historic fire lifts. In general, this is because of the higher standard of protection now provided to firefighting lifts. I will now explain the lift replacement works. A complete replacement of the central lift system was undertaken in 2005. From reviewing the specification within the health and safety file prepared for the works, the standard of lift specified then was consistent with the historic fire lift standard and not the firefighting standard applicable in 2005. Then further modification works were also undertaken during the primary refurbishment. The scope of this modification was to increase the number of floors served by the 2 central lifts. During these works, the lifts were not upgraded either to the applicable firefighting standard. The scope of the lift refurbishment works in 2005 was substantial. It included replacing all associated equipment and machinery. New lift cars were installed. New lift landing doors were installed, call points and controls. The openings in the lift shaft were also increased in width. The lift was not at this time upgraded to serve level 1 and 3 and therefore continued not to serve every floor of the building, as is required for a firefighting lift. Later, during the primary refurbishment, new openings in the lift shaft were created on level 1 and 3 as a way to access the new residential flats on these levels. Therefore, after the primary refurbishment, both lifts could be used to access every floor, as is required for the firefighting lift standard. During 2005, the 2 lift cars were increased in size and capacity. The plan drawing on the left indicates the smaller original lift car, and on the right the larger replacement lift car. The openings in the lift shaft on every floor were widened to increase the clear entrance of the doors from 800 to 880 millimetres. The new capacity of 900 kilograms did meet the minimum standard for a firefighting lift. The specification for the 2005 works also required a firefighter control switch to be installed. A firefighter control switch is required for both a fire lift and a firefighting lift. I observed 2 firefighter control switches in Grenfell Tower, photographs of which you can see here. One at ground level where it is required, as this is the firefighter entry point to the building. I observed the second switch at level 2. This is not the firefighter entry point to the building. The 2016 fire risk assessment states that the control switch should then be changed from level 2 to ground level, indicating that prior to 2016, the fire control switch at level 2 was operational. The 2005 specification also included an emergency intercom system, which is required for a firefighting lift only. However, I've not yet been able to observe whether this system was installed on site. Therefore, following the 2005 and 2012 to 2016 works, the lift specified for Grenfell Tower contained a number of fire safety features, which I have highlighted in green in this illustration. These provisions satisfied the requirements for a historic fire lift. They did not satisfy all of the requirements for a firefighting lift as existed at the time of the 2005 and the 2012-2016 refurbishment works. Key features that were required to meet the standard but which were not specified are: a secondary power supply was not specified. Electrical schematics showed it had an independent power supply. The exact cable routing is not known. The lift landing doors were not specified as requiring any fire resistance when they were required to have 60 minutes fire resistance. No water protection measures were specified for electrical equipment within the lift car and well. An escape hatch was not specified for the replacement lift car. As the lifts were not specified to meet the standard of a firefighting lift, they could not therefore also be relied upon for evacuation, because, as it states in approved document B, where a firefighting lift has been provided to satisfy requirement B5, this can be utilised as part of a management plan for evacuating disabled people. Any such plan should include a contingency for when the fire and rescue services arrive. And that ends my lift talk.
Thank you very much.
Will I keep going?
Well, what is your next
Well, I have.
topic, and how
I can
long do
move
you,
on to doors now, or have a break and do doors later.
how long do you think doors might
Doors
keep us going
runs
for?
for
15 minutes.
15. Well, about 12 minutes.
Yes.
12 to 15 minutes.
We could do the 15 minutes now and then break for lunch.
Do you want
if
to do
that's
that?
convenient.
Yes.
Is that okay?
Shall we do the doors?
Yes, I'll just do the doors. Yeah.
Okay. Thank you.
I will now describe the works that were undertaken to fire doors in Grenfell Tower in 2011. I've described the role of fire doors in protecting door openings in compartments. Compartmentation is the primary fire protection measure for the single safety condition, the stay-put strategy. Where doors are required within walls requiring fire resistance, those doors must be self-closing or lockable fire doors according to the statutory guidance. There are various performance requirements that they need to achieve and must be subjected to fire testing to confirm these performance requirements. These requirements have changed over time since 1974, when the tower was built. Fire doors are tested as a whole assembly, which is in the state it is installed in a building. So importantly, this includes the hardware, glazing, seals around the door and several other components. These components are shown in the next slide, but before I move on, to show that a door assembly meets the required standard, the door assembly should be in accordance with the specification or design which has been shown by test to be capable of meeting that performance, or have been assessed from test evidence against appropriate standards, or by using relevant design guides as meeting that performance. These are the components of a fire door assembly. In Appendix I 2.2 of my report, I listed out 44 features that form a fire door. Of these, the principal components are the door leaf, the door frame, the architrave, which is a trim that serves to mask the joint between a door frame and the surrounding structure, a self-closing device, an intumescent fire seal, and a smoke seal, which is for the purposes of restricting the flow of cold smoke. Fitted to the door leaf is various ironmongery, which includes latches, locks, letter plates and handles. As indicated in this diagram, everything together is known as the door assembly, and every component is relevant to the fire performance of the system. I will now describe the location of the specific doors in Grenfell Tower, which were required to be fire doors. These are the fire doors required to maintain the compartmentation to all flats, the stairs, and the openings onto all the lobbies and other risers. Within the core of Grenfell Tower on levels 4 to 23, all of the fire doors were installed in the partitions forming the core of the tower. To indicate each of these, a diagram of the protected lobby and stair is shown. First, flat entrance fire doors. The front door of every flat should be a fire door, as it separates the flat from the protected lobby. There are 6 of these doors per floor on levels 4 to 23, and they are indicated in yellow. The lift shafts must also be a separate fire compartment and should be separated from the protected lobby, as the lift doors open onto the protected lobby. The 2 doors to the lifts at each lobby therefore should achieve a specified fire resistance, as shown in yellow here. The refuse chute room is also required to be a separate fire compartment, and so the single door to the refuse chute room on every level is required to be a fire resisting door, and that is it located at the yellow marking there. Finally, the single door to the protected stair at each level. The protected stair is another separate fire compartment, and so is also required to be provided with a fire door. In 2011, a programme of fire door replacements at Grenfell Tower was undertaken. This 3D image of Grenfell Tower indicates in the model the flat entrance doors on a typical level. Zooming out to the extent of the full screen, you can see the doors that were replaced in the tower and the doors that were not replaced as part of these works. That's their locations. The programme of work was undertaken by the TMO to replace the front door of dwellings occupied by Royal Borough of Kensington and Chelsea tenants. 106 fire doors appear to have been supplied and installed by Mant's Master Door to replace the main flat entrance doors. This is based on their door replacement schedule, which included 104 tenanted flats and 2 leaseholder flats. Therefore, 14 fire doors that were not replaced consisted 12 leaseholder flats and 2 tenant flats. These works did not specify new doors for the lifts, stairs, refuse chute room or any other riser in the tower, nor any of the doors on levels ground to 3. The standard for the fire safety performance for the flat entrance fire doors at the time of installation is described in Approved Document B. The key requirements are integrity fire resistance of 30 minutes when tested to the fire resistance test, British Standard 476 Part 22. The doors should be fitted with smoke seals, restricting air leakage around head and jambs. No glazing is permitted unless that glazing has been demonstrated to achieve an insulation performance that is equivalent to the integrity performance of the door. A self-closing device is required. The fire door should only be fitted with locks readily openable from the inside without a key. Regarding glazing, any door containing glazing should have been tested with the glazing in place, or an assessment have been made to show that it would meet the required performance. The glazing must have insulation fire resistance in addition to integrity fire resistance, because Table A4 limitations on the use of uninsulated glazed elements on escape routes as presented in approved document B, states, no part of the wall or door leaf between residential sleeping accommodation and a common escape route of a single stairway building can contain uninsulated glazing. The fire door product to replace the flat entrance doors in Grenfell Tower was Sure Door GRP, as manufactured by Mance Master Door Limited. The brochure for Sure Door GRP doors describes the doors as a fiberglass composite door, which was successfully tested for the integrity and stability criteria for 30 minutes. The brochure does not state that the doors have been tested for coal smoke leakage as required, nor for the insulation component of fire resistance. The photograph on the left shows the exact single test specimen that was used to achieve those test results. It does not feature any glazing or a number nameplate, for example. It does feature a specific latch, lock, letterbox, handle and spy hole. The self-closer on the tested specimen was externally mounted on the door. In Grenfell Tower, the Mance Master Door specification sheet specified 58 unglazed Sure Door fire doors were installed. An example I observed is shown on the left. 48 glazed Sure Door fire doors were installed. An example I observed is shown on the right. Sorry, I got that mixed up there, on the right. With regard to the ironmongery, the Mance Master Door specification sheet specified different locks, different letterboxes, different self-closing devices and hinge types to that provided for within the fire test. Regarding the 14 flat entrance doors which were not replaced, there is little evidence available regarding those doors as they have mostly been destroyed by the fire. In considering if those doors were the originals as installed in 1974, it is now useful to note that the requirements were different at that time. The main differences for a flat entrance door at that time were self-closing devices were different. This could be achieved using what's called rising butt hinges, which are wedge-shaped hinges shown in this photograph. These are no longer acceptable. Integrity rating of 20 minutes. This is 10 minutes less than the 2011 standard. A 12mm rebate was also required to prevent smoke spread, which I will now explain. In both 2011 and in 1974, fire doors have incorporated measures to stop the spread of smoke. In 1974, this was in the form of an overlap between the door and the frame, known as a rebate. In the picture on the left, the door would swing into the frame away from the viewer and be stopped from swinging any further once in the frame by the rebate. The depth of rebate required was specified, rather than a limit on the rate of air passing through the door. In 2011, preventing the spread of smoke was, and still is, usually accomplished by smoke seals, which could be brush-like or rubber-like strips around all sides of a door that are designed specifically to seal airflow around the edges of a door. Regarding the stair fire doors, I have no records of replacement works to the stair doors. Therefore, I have assumed that the stair doors were the original doors as fitted in 1974. Again, comparing the requirements for stair doors in 1974 as opposed to the requirements set out now in approved document B. In both 1974 and 2011, stair doors were required to be self-closing. In 1974, an integrity fire resistance rating of 30 minutes was required. Current standards would be for a 60-minute integrity rating. In 1974, a 25mm rebate was required. The current standard would require smoke seals with prescribed limit on airflow. I observed in Grenfell Tower that the rebate was 12mm, not 25 on the stair fire doors. A 12mm rebate would indicate that this is a 20-minute fire door. To summarise the fire door provision within Grenfell Tower on the 14th of June 2017, 106 of the 120 flat entrance doors were replaced with Sure Door GRP doors. The remaining 14 doors comprised of leaseholder flats and 2 tenanted flats. They are assumed to be original doors, however few remain to be investigated. The lift landing doors were replaced in the 2005 lift works with no specified fire resistance. The stair fire doors have no documentation or records defining any replacement, so it is assumed they are the original doors as installed and appear to have fire resistance of 20 minutes. For the refuse chute room doors, currently no documentation or records of their replacement are available, and so it is assumed they are the original doors as installed in 1974. Fire doors are a crucial element of the stay put strategy, as they represent an opportunity for weak spots to form in the fire resisting partitions that separate a flat fire from occupants either on that floor where the fire has started, or occupants in flats above the floor the fire has started. Fire doors are therefore a building regulations requirement as a passive fire protection measure. Faulty fire doors mean faulty compartmentation, and compartmentation is the primary basis of the stay put strategy. Thank you.
Thank you very much. Now, you've been speaking almost non-stop for quite a long time. Would you like a break now?
Yes, I would.
Yes. Well, I'm not surprised. Thank you very much, and
Thank
you've given
you.
us a lot to think about.
Thank you.
If we resume, we will break then in a moment. It's a little earlier than usual. If we resume at 2 o'clock, is that going to give you enough time to finish after?
Fine. Absolutely fine.
Right, good. Well, thank you very much. In that case, we'll rise now and resume at 2 o'clock, please. Okay.